sensing elements. Doped sensing elements manifested low hysteresis and better response and recovery time compared to the sensing elements of undoped ones. So here I am presenting now a case study of experimentation of pure WO3 and silver doped WO3 prepared through soft chemical route. One such part I am presenting to you after giving this introductory remark, which was quite long, but because you understand what now I am going to deal with, to make you understand these things, I have given that background quite in detail. So what we have done, we have seen nature of changes analyzed because of doping, morphological and crystalline changes studied, change in response to humidity study. We have used a scanning electron microscope and X-ray diffraction we have used. Humidity sensing studies of WO3 and AG loaded WO3 have been investigated. What we have done, performance characteristics such as sensitivity, reproducibility, and response time have been recorded and correlated to its microstructure. Now we have taken one such route, soft chemical route for preparation of the sample that I am presenting here. WO3 nanocrystalline powders were obtained by soft chemical route based on tungstic acid. 10 gram tungstic acid were dissolved in a 50-50 volume mixture of methanol, water. To stabilize the precipitate, 25 milliliter of water was further added gradually. The mixture was heated at 80 degrees centigrade for 24 hours under continuous magnetic steering in air and then dried by further heating at 110 degrees centigrade, leading to tungsten oxide hydrate. This needle annealed in a furnace at 300 degrees centigrade for 3 hours to obtain nanocrystalline pure WO3. To make the sample of pure WO3, 10 weight percentage ethyl cellulose has been added as binder to pure WO3. Now this soft chemical route we have taken from the literature, and later we have added 10% ethyl cellulose from our side to make the sample stronger. So these methods are available in literature. Now then we have added 1 weight percent of AZ metal powder to pure WO3 obtained through the above method. The two powder mixtures were grinded separately for 3 hours. Now mind it, if you are grinding it for 1 hour, you are grinding it for 2 hours, grinding it for 3, you will have a completely different morphology of the sample. So everything has to be monitored. Now, these powders were given pellet shape in a hydraulic press. Then they were annealed. The result that I am going to give you, that pellet sample had 12 millimeter diameter and 3 millimeter in thickness. Now let us, for example, let us say if it is pure WO3, we will call it W, and if it was AG doped WO3, we will call it AW. Now, principle of operation. I will give you the principle of operation here first so that you can have an understanding of how it operates, although the exact chemical reactions are somewhat complicated, but it is a simplified picture that I'm presenting. WO3 is an N-type semiconductor. You can have, for example, NiO, which is a P-type semiconductor. So WO3 is an N-type semiconductor. Hence, sensitivity to humidity is a result of electronic conduction. A semiconductor drying oxide of WO3 nanocomposite is brought into contact with the humid air. Water molecules chemisorb on the available sites of the surface, oxide surface. The adsorption of water molecules on the surface takes place via dissociative chemisorption process, which may be described in a two-way process. क्या क्या है? एक है ये reaction पहला हुआ. Molecules get absorbed on gray surface, reacts with lattice W as this one. ये एक reaction है. Then O3 is lattice oxygen and V0 is the vacancy created, right? And then we have this oxygen vacancy, O2 minus a V0. W ionized oxygen displaced from the lattice reacts with the hydronium ion coming from the dissociation of water molecules to form a hydroxyl group. WO3 has electron vacancies. Hence, because of this reaction, the electrons are accumulated at the WO3 surface and consequently, the resistance of the sensing element decreases with increase in relative humidity. That is that. Now, that is a simple picture. What exactly happens if Ag is loaded to WO3? The sensing mechanism of metal oxide based gas sensors lies in the change in oxide resistance resulting from physisorption, chemisorption, and catalytic reactions of gas phase species at the surface of the semiconductor device. The catalytic properties of WO3 are determined by the ability of the tungsten ions to change their valence state upon reduction, etc. In a stoichiometric WO3, the tungsten oxide has 6 plus valence with 5D shell empty. There are no cations. Now, this is how the stoichiometry changes when Ag is added. I will not go into the chemistry of this one right now. And then this is all explanation, and these all explanations we have already given to the journal, and it has been already been published in one of the prestigious journals, IEEE Sensors. So this is the mechanism that we have developed, we have explained in the literature as to how it happens. So this chemistry I'm not going in detail, but how the surface chemistry changes, how the charge density changes surrounding the, let us say, grains and grain boundaries, etc. These all mechanisms are mentioned, and therefore, finally, the resistance will change because of this. Finally, because of the charge density changing, the sensor will respond. Now, so I will directly come down to the graph. Humidity graphs for AW. You can see Ag doped WO3. This is how it responds to. If you have relative humidity on the x-axis and resistance on the y-axis, and at different annealing temperatures we have done it, 400, 500, 600, 700. And you can see from here that initially the fall in the resistance in the range up to 50% relative humidity is very good for this material. And after that, the fall is slow. That means it is highly sensitive in this region, and it has lower sensitivity in the higher region. This particular material, Ag doped WO3. And if you see the same one, you can see from here. What do you see? All the graphs show from 20 to 50% R, there is a rapid decrease in the value of resistance, while 50 to 90% range, the fall of the resistance is low. 20 to 50% range, sensitivity of sample is very high. And this is the sensitivity chart that you can see. Annealing temperature is 400, percentage range of relativity 20 to 50%, and 50 to 90%. Here it is 2.83. Here it is, if you are adding Ag, then it is 3.46. Generally, you will find that the sensitivity is increasing on loading by the silver items. But mind it, it is the role of annealing temperature is also very important, because in the lower temperature, annealing lower temperature, the changes are not much in the sensitivity, but when you go for the higher range annealing temperature, the change is very large. Sensitivity increases very much. You can see from here that this is for the pure WO3 that we have, and this is for silver doped WO3. This is when we are increasing the relative humidity. This is when we are decreasing the relative humidity. That is, we are seeing the hysteresis between the two. And this experiment has been done after 4 months. The sample has been tested, kept it for 4 months, and the experiment repeated after 4 months. C6 is after 6 months. And similar experimentation for Ag doped WO3, initial range of increasing cycle, decreasing cycle, cycle increasing after 4 months, cycle increasing after 6 months. You can see here that for 400 to 500 degrees centigrade, the change in sensitivity from W, that is pure WO3, to Ag doped WO3 is not much. But if the temperature is 600 and 700 degrees centigrade annealing temperature, then there is a significant change in the sensitivity, and that we can show over here. For annealing temperature 400 and 500 degrees centigrade, there is not much change in the value of sensitivity in the range 20 to 90% RH for sensing element of Ag doped WO3 as compared to sensitivity for, that means the sensitivity that was for pure WO3 does not change much when we are doping with Ag. But if the annealing temperature is 600 to 700, then there is a significant change in the sensitivity when Ag is loaded. And the sensitivity has increased for 700 degrees centigrade by 2.4% from, you can say, WO3 to Ag doped WO3. You can see a graph between sensitivity versus temperature. That is, W is for the pure one, and this is for the Ag doped WO3. Sensitivity is increasing because of the loading. This graph you can see. A is for WO3 and hysteresis, A is for increasing cycle and B is for decreasing cycle. You can see that after large number of operations, we can see that the relative humidity becomes, the hysteresis becomes a small in WO3, and even in Ag doped WO3, the hysteresis is small. And if we can quantify them, then we can say all sensible sensing elements have acceptable hysteresis value. Hysteresis is found to decrease with increase in annealing temperature. For WO3, hysteresis decreases 5.8%, 5%, 3.43%, and to 1.4% when the annealing temperature goes from 400 to 700. For AW, hysteresis is small. There is not a definite trend, but certainly the hysteresis from the values for WO3 to Ag doped WO3, hysteresis has decreased. There is a definite decrease in hysteresis between when the Ag is loaded in WO3. Now, aging graph for sensing element, you can see A for increasing cycle, C4 after 4 months, and C6 after 6 months. You can see that the aging has been reduced and the graphs are following almost the same trend. Results: Ag doped WO3 annealed at 700 degrees centigrade. The values are generally repeatable within 2 to 3% and within 1% for Ag doped WO3 in the 20 to 94%. The corresponding values for sensing element of pure WO3 is also within 2%. So these are very acceptable results that your error or the aging is within plus minus 2 to 3%. These are the XRDs to understand what exactly the phenomenon has gone through. This is for WO3 and this is for Ag doped WO3. XRD result. For WO3, you are getting crystalline size of 12 to 72 nano. Like I said in the beginning, when we are talking about nanotechnology, then the size should be between 0 to 100 nanometer. The crystallite size for Ag doped WO3 is 19 to 73. So the range is in the nanometer range. XRD shows what types of formations have been there. Response and recovery times have decreased because of Ag loading on WO3. Now, these are the conclusions that what happens that the sensitivity increased on loading, the hysteresis decreased, the aging decreased because of Ag loading in WO3. And one result that I have shown is about 700 degrees centigrade annealing temperature. Now, after this experimentation, what we did, we increased the percentage of Ag in WO3. The earlier results were for pure WO3 and 1% Ag doped in WO3. Now we are increasing it to 4%. 1%, 2%, 3%, 4%. So what exactly is coming up? Now, even Ag doped WO3 for different percentages, they have all been published in very good International Journal of Applied Ceramics Technology, Journal of Materials Research, etc. So for 700 degrees centigrade, you can see the trend. Resistance versus relative humidity. This is for pure WO3. This is for 1% Ag in WO3, 2% Ag in WO3, 3% Ag in WO3, 4% Ag in WO3. What do we find? Maximum sensitivity of 2.38 megohm per percentage RH has been found for sensing element 4% of this one. When you add 4%, then maximum sensitivity is this much. And from 0% of Ag in WO3 to 4% of Ag in WO3, the increase in sensitivity is by 11.34%. Now, next part is whatever you are doing, you have to create knowledge also. That is, you have to see some kind of mathematical relations, some formulations have to be made, some explanations, physical explanations, chemical explanation has to be given for what you have done. Only experimentation will not do. So what do we see? That sensitivity versus percentage doping is fitting onto a polynomial of degree 3. Then we have desiccation graph. Then hysteresis. Again, hysteresis is decreasing, very small. Of course, not giving some trend, but that is well below 2%. The maximum change in the value of sensitivity for decreasing cycle over increasing cycle are below plus minus 2%. This is aging. After 6 months, the values of aging are found to be 0.4%, 0.48%, plus minus 1.4, plus minus points. So you can see the aging is very, very small after 6 months. That is, the sensor is able to be operated even after 4 months and 6 months. So this is repeatability over a period of time. So the maximum aging for our samples over a period of 6 months is within plus minus 2%. Now, regression least square feet with respect to polynomial of third degree E and fifth degree established coefficients of various powers of X here with respect to Y, resistance is tabulated. You can see if you are doing some polynomial or regression analysis, then polynomial coefficient that we found were these ones. Relative humidity versus resistance. Then polynomial coefficients of degree 5 were established for some samples, and these are the coefficients. Relative humidity versus resistance. Response recovery times for 0, 1, 2, 3, 4% of AG were 94, 75, 80, 74, 72. So the response times were decreasing with increase in the loading percent. Recovery times were also decreasing. Now then, surface morphology is done by the scanning electron microscope. Despite giving the result directly, I am just showing what a scanning electron microscope is for the convenience of the students so that they may try to study scanning electron microscope. In a scanning electron microscope, a set of scan coils move on the electron beam across a specimen in two-dimensional grid fashion. This is their structure. And I suggest, we do not have much time to go into this, but a scanning electron microscope can magnify the surface viewing by around 1 lakh times. That is the advantage of a scanning electron microscope. And if in place of a scanning electron microscope, you are using a tunneling electron microscope, then it can amplify your surface analysis by 5 lakh times. So you must study what is a scanning electron microscope, what is a transmission electron microscope for your convenience if you want to study any field that is related to the material science. Now, this is the difference between TEM and SEM. Now, this is just I have shown you what is a scanning electron microscope and how does it study the surface and what kind of surface comes up. So this is the scanning electron microscopic study of pure WO3, that is sensing element of WO3. You can see the surface morphology of that one, WO3. Then 1% of AG doped in WO3. This is the surface morphology. You can see that voids, etc., have started coming up because of the addition of the AG. And of course, chemical reactions, etc., are there that I'm not going into detail, but these are the voids coming up, leading to more adsorption of moisture, or if you are sensing a gas, then gas. Then for 2%, you can see how the crystals are being seen clearly visible. Then you have, for 3%, you can see the crystallites are very, very visible over here. And you can see the range is, the small range that we are seeing over here from here to here is 300 nanometer. So the crystallites are very, very small to slightly larger also. And here the magnification is, you can see 30,000 times. Then 4, this kind of surface morphology is visible by SEM, scanning electron microscope. So SEM, what does SEM micrographs of sensing element of pure WO3 manifest beautiful mountain-like patterns, whereas SEM micrograph of sensing element of AG doped WO3 manifests great distribution in grain size and increasing crystallinity. Scanning electrons micrographs show flakes of the pure WO3 and AG doped WO3 scattered throughout, forming a network of pores that are expected to provide sites for humidity absorption. SEM micrographs show that the sensing elements manifest porous structure having granulation tendency. Similarly, they have a grain-like morphology. WO3 mixed with AG powder has a grain-like morphology. Upon treatment to heat, clusters of AG are formed at the surface of WO3 grains. AG WO3 bronze forms at the interface between the grains and clusters due to diffusion of AG in WO3. Given the tendency of the noble metals to form clusters at the surface of metal of grains, the actual increase observed in grain size distribution with increase in percentage of AG can be associated with increase in, means when you add some noble metal, there will be a tendency to agglomerate. And when they have an agglomeration tendency, large number of voids, conduits, pores, porosity will be created, leading to much more higher sensitivity. So that is about the SEM studies, the grain size distribution. You see, sensitivity is found to increase with increase in percentage loading of Ag. Sensing element of AW4 has the highest crystallinity as well as maximum void concentration. Sensing element of AW4, 4% Ag doped in W3, annealed at 700 degrees Celsius, shows maximum sensitivity of this 4%. Average hysteresis below plus minus 2%. So similarly, this was the gradation analysis data has been done. And if just for the case of it, I have shown a P-type material also. And this has just been published in Sensors and Actuators. So NIO-based humidity sensor, you can see from here. And because you can see if it is N-type, because of the contribution of electrons, the resistance will decrease. And in the P-type, because of electrons being taken out from the surface, the resistance will increase. So if you are increasing the relative humidity, the resistance is increasing for P-type material like NIO crystal. And this is how it is, sensitivity versus relative humidity. And this is a comparison. You see, from various sources, I have taken this sensitivity reported in literature. For example, NIO, SNO2 electro, they have sensor fabricated through electrospinning technique. Humidity range was 0 to 100 and sensitivity was 3.25 kilo ohm per percentage. Here, by this method, this material 100 kilo ohm per percentage. Here, by this method, 118, 124 kilo ohm. This and all the materials that we are doing, Ag doped WO3 solid state reaction load, this is the range of relative humidity, and we are getting 2140 kilo ohm per percent. You compare these ones, how high sensitivity we are getting. Cu2O ZNO, that is in IEEE sensors, again published here. There, this much is the kilo ohm per percentage sensitivity. For this one, we are getting this, and for MnO to ZNO solid state reaction, we are getting this much sensitivity. So we are getting a very highly sensitive material for sensing application. Only thing is that we are trying to control the you can say the aging. We are trying to control the hysteresis. We are trying to improve upon the response recovery time, etc. So various parameters of the sensors have to be looked in for improvement through experimentation, through trial and error, and some optimization has to be done. These are certain publications of 21 only. So I must thank you everyone for kind attention. I cannot go into details of every aspect, but I have tried to give you a brief of, let us say, of the brief introduction about. I have tried to give you a brief introduction about what we are doing here without going into much of the chemistry, much of the physics behind it. I've tried to give you, you can say, an impression of how things are working. I have tried to give you an impression of what are the fundamentals you need to know to understand the topic of research that we are doing. And I have also tried to give you a vision as to if you want to enter into this area for work, you have plenty of scope despite large number of work, lot of works have been reported. So advantage is you have a lot of report to understand what is going on. And the advantage is you have a lot of scope to work something on new. This is about metal oxide sensors and some results from our lab. Thank you very much, sir. Thank you very much.
Thank you. Thank you so much, sir, for that wonderful and knowledgeable presentation. And if sir allows, and if sir has got some time, we can have a few questions from the side of audience, if you allow, sir.
Yes, yes, why not?
Okay, thank you so much, sir. And I request the participants to kindly write down the questions in the chat box. And in the meanwhile, we have a question from Mr. Hariom Pawar. And he wishes to ask that how can the porosity be calculated of pellets?
Oh yes, porosity. Actually, there are instruments also for calculation of the porosity. And there are some crossbar methods also for calculation of porosity. You go to the literature and just put on the Google calculation of porosity, you will get the formula also. And large number of sophisticated instrumentation also come up. So that is an easy step right now. So you can easily measure the porosity. Yes, of course.
Thank you so much, sir. And because already it's been the time, so the remaining questions shall be mailed to sir via email, and definitely sir would.
Actually, I've been informed that I am right now the head of the Department of Physics, and we also have Science Day celebration beginning 2 o'clock in our department. So after the lecture, I have to rush to my department where people are waiting for me.
Oh my God! Thank you so much, sir, for your valuable.
No, there is nothing to say about Sherry. There is nothing. So it was all planned.
Thank you.
Of course, it was a nice opportunity to talk to Dr. Ashish Verma and know about him.
Thank you, sir.
He has said that he's working in some similar area. So I don't think that I'm going to spare him at this moment only. We will have a long relationship also.
Exactly, sir. Exactly. That's what I want to say.
Yes. And even the head of the department.
We need your help because I am also working on some sensing material.
Yes,
So
we'll talk on email.
I will keep in touch with you.
Share certain papers.
Oh, yeah.
And about your head of the department, because he happens to be the counterpart of me in terms of I'm also the head of the department here. So we can have an exchange of lectures at the two places.
Oh, why not, sir?
Why not? Sure,
sir. We'll plan accordingly. And it will be my pleasure to invite some people here at the University of Lucknow.
Exactly,
sir. And head of the department, Sir Professor Ranveer, you may be getting some of my, let us say, thesis of some of the students.
Right.
Sure, sir.
Very opportunity to have exchange of all of these things.
That's sir.
That is the purpose of this webinar. I suppose Dr. Ashish Verma had in his mind.
That's why we find out you, sir.
It's my pleasure, sir. It's my pleasure. It's my pleasure.
Okay, take 1 minute for vote of thanks, Arun.
Okay.
Thank you, sir. And now this is the time, as sir said, for the vote of thanks. So I request Mr. Arun Kumar Singh, sir, please.
Thank you, Sari. Very good afternoon to our eminent speaker, sir, respected teacher, participant, and entire webinar committee. It is my privilege to have been asked to propose a vote of thanks on today's webinar. On behalf of Physics Department and entire university, I would like to thank the founder of this university, Dr. Harisingh Gour, sir, and on my behalf, I extend a very hearty vote of thanks to Honorable nominee Vice Chancellor of this university, Professor J.D. Ahiman, who took time out from her busy schedule to grace this occasion. I would like to thank our eminent speaker, sir, Professor N.K. Pandey, sir, for delivering excellent presentation on metal oxide nanomaterials for sensing application and making this webinar a very meaningful and interesting. I would like to express our deep gratitude to the Dean, School of Mathematical and Physical Sciences and convener of this webinar, Professor Ashish Verma, sir, for organizing such a wonderful webinar. I would also thank to our head of department, Professor Ranveer Kumar, sir, for his guidance and moral support. I am happy to express vote of thanks to our teaching, non-teaching, and colleague research scholars. Finally, I thank to the wonderful participant who turned up in such a great numbers. Thank you so much for your cooperation. Thank you. Once again, I thank all for their cooperation and support. Thank you, sir.
But sir, our thanks is left for Sherry.
Oh, yeah.
For nice conduct of the program.
Oh, yeah.
That's really sweet of you. So, thank you.
It is a big thanks to all of us, to Mrs. Sherry Nair, who gave a very nice and take the program very nicely up to the end. So thank you, Sherry.
Thank you so much, sir.
Thank you very much, sir. Thank you.
Okay, sir. Thank you very much. You have another program in your department.
Thanks.
Okay.
Okay.
Thank you so much, everyone. Link for feedback form has been provided in the chat section. All the participants are requested to fill in the form so that e-certificates can be distributed thereafter. Thank you so much. Have a great day ahead.